Yeah, thank you. So, pleasure to be here. Just let me pull this up if it works. Okay, great. So, as they invited me here, we had a conversation. They asked me, well, I am a professor at the EPFL. I work in physical robots, artificial intelligence. And so they asked me, what is next? Where is this going? What are the bottlenecks? And so my talk is going to be about this thing. So it's a bit more, what is the technology which I think is missing today and where we are going? So you see drones here. This is an artistic rendering of what we do in the lab. We build biologically inspired machines, not only drones, all sorts, but a lot of drones. We look at their sensors, at their bodies, at their intelligence, and how they work together. So we do a lot of swarm robotics as well. And so, the question is, what is, are we going to get RobotGPT? We have ChatGPT, generates text. Are we going to have generation of behaviors for robots? Because a behavior is just a sequence of sensors and motor commands, and sensors and motor commands, just like words have a structure that has a temporal sequence. So in principle, it should be possible. And well, over just a couple of years, these are a little bit technical slides, but just over a couple of years, there have been two, I think, interesting developments. One is where people use large language models to generate programs and instructions for robots, drones, so that they do a task. For example, large language models can go on the internet, get a program for a quadrotor, and if a person say, go north, the large language model will develop the program that drives that drone north. And so out of this, for example, they can instruct large language models to create programs that control the position of several drones in the sky. They simply say, generate a figure like Saturn, then become a sphere. And all these robots will be instructed by large language models that take software from the internet to do this. But this is in simulation, and this is just an interface for large language models to develop or to pick up programs that have already been put on the internet by people. Something more interesting happened very recently, as has already been mentioned multiple times, is vision language action model. So this is an image from this paper from Google, was 2023, and this thing is developing very fast. This is the fast developing field, in my opinion, in terms of RobotGPT today. And essentially, what is happening is that they use a visual language model. It takes as an input an image and an instruction from a person. For example, it could take an image of some cakes, an instruction from the person, and they also have a sequence of control commands from a robot doing that particular action, for example, picking up a strawberry and putting it into a cup. And that sequence of actions from the robot, like a robotic arm, is encoded in a token similar to the language, put in input to the neural network, which generates in output a sequence of robot commands using the same type of encoding, which is then decoded in robot commands. And this is what this robot does, essentially. It generates these motions, and the beauty about this is that essentially you use the camera of the robot to look around and tell, for example, pick up a banana and put it on number 3. And the robot understands where number 3 is from the visual language models and translates that command into a sequence of robotic actions. But, as the authors of Google X said, these VLA models do not generate new skills. They just pick skills from robots that already have them, that are codified in sequences of control commands for that specific action. All they do is that they generalize to new images and to new contexts. There is no new language or no new skills acquisition, so to speak. Not only that, but if you look at these robots for which these control commands have been tokenized, they are very simple robotic manipulators that are described by mathematical equations and sequences, like move to point A, then to point B, then to point C. There is no dynamics, there are no muscles, there is no acceleration, nothing at all. So essentially, this robot does not understand what it does. It is just associating a sequence of commands that have been already pre-programmed in the robot. Not to speak that The large language model, or the vision language model, is a huge 30 billion parameters code which stays on a cloud computer which communicates with the robot wirelessly or via cables. So how do we get real robot intelligence, robots that can actually learn new skills? There are very few skills or very few behaviors that have been codified in tokens. Although there is a library which is growing, many people around the world are contributing to this library, it is still sequences of control commands. Well, how do we generate new behaviors? As soon as you have a more complex robot than this manipulator, like a quadruped, it's very difficult to control this program by mathematical equations or to control them. So people use reinforcement learning. The robot interacts by trials and error with the environment, and then it learns by mistakes how to become better. Now, this has been around for 35 years. Nothing has changed in this field for the past 35 years. But what has changed is that over the past 4 years, big simulators have appeared. So today we have the possibility of simulating, I'm showing the work of my colleague Marco Hutter at ETH Zurich, we can simulate on parallel computers, realistically, rigid-bodied robots that learn in parallel in the simulator to solve problems on their own. So they learn tasks on their own. This has made a huge change. The algorithm have been around 35 years. My colleague Davide Scaramuzza, again from University of Zurich, neighbor to ETH, published in Nature the first drone, autonomous drone beating human drone racing champions. Again, using reinforcement learning trained in simulations. But simulations are hard. And bodies that have these type of models that can be simulated are very few. Are quadrotors, are legged robots, and maybe some bipeds. What if we want to reproduce the capabilities of this drone, which is a biological drone, as you can see, which uses the entire morphing of the body together with integration of sensors of information coming from vision. Here, we need to understand how this bird uses the feathers, how it interacts with the air. You talk to biologists, how do the birds turn around trees so rapidly? What type of motion of wings and tail they do? They do not know, because they cannot study these birds in lab environments. They are too smart, they fly outside. You ask fluid dynamics, what are the laws of fluid dynamics that these birds use? They do not know, because the best models today we have are valid for fixed, rigid wings machines, aircraft. So the best way of moving forward and generating a new family of robots, and here I show the example of drones. I could give you the example of soft medical robots that interact with our intestine. It's the same problem. We don't have models or simulators for training them. So the best way we can do is to build machines that look like this, expose them to wind. This surface is a open wind tunnel that blows air in a controlled fashion. And we can measure the forces using a sensor attached at the tip, at the bottom, at the belly of the robot, to measure all the consequences of the wind as the drone moves. We can do that into what I call the robotic aerodynamic characterization platform. The robot is positioned in front of the wind. There is a robotic arm that mimics all the possible attitude and flight condition of the drone in the air, while the drone moves the wings in all sorts of possible conditions, and we have motion tracking camera all around that monitor the motion. All this data go to a computer, and the computer creates a model. And with this model, then, we can develop control structures that can fly just like birds. We still have a propeller for generating thrust, but the drone just flies using the wings. And we have done that thanks to these data-driven models. We are now moving towards things that today robots cannot do, like this bird can hover in the wind, harvesting energy from the environment. We have now our models that we have used data to learn our models. We can first train them with the reinforcement learning in simulator to go to a point, the yellow point there, by moving the tails and the wings. And then we can take them to our lab. We start blowing wind. You see there is a safety cable there, but essentially now the drone is flying stable against the wing as if it was in the air, using the learned policies in simulation. And you can also simulate wind gust by hitting it, and you will see that the drone automatically restabilizes itself. This would have been very difficult to program. We could only do it by means of learning in simulation. we need new simulations. So time is running out. Sensors are important. We do a lot of work in neuromorphic chips because animals, birds, insects, even ourselves, we do not simply record the photographic images. We record events. And so these new neuromorphic cameras are used now on this drone, which is not an avian-inspired drone, but to regulate the altitude and safely land in day and night using only few lines of code, not billion of parameters. I'm talking about 5, 6 parameters. My final slide is, so will we have RobotGPT? Yes, RobotGPT like VLA models. We already have some. We need more learned skill sets, and I'm pretty sure that we will have them pretty soon. But there will not going to be a generic model here. Here I have to disagree with my former colleague. I think we will have for different bodies requires different action sets. We will have a VLA for robotic manipulators, a VLA trained on quadrupeds, one on drones. But if I had a lot of money and I would invest, I think there are 2 bottlenecks today. The first is that we need to gather new skill sets from robots. There are very few skill sets out there. And so we need, and learning physical system is underestimated. I would invest a lot in new type of data-driven simulation, which in our community are called neural simulators, physics-based neural networks that simulate the world, that allow us to do a new type of science. And we need to invest more in better understanding what learning is. Reinforcement learning is only part of the story. It takes millions of cycles. We need to understand how the learning dynamics, the learning architectures, the interplay of body morphologies and brains work. And for example, just to reconnect with what Antonio Damasio was saying this morning, quite interestingly, homeostasis is a very good driver of adaptation. There was a scientist called Ashby who wrote in 1960 a book, Design for a Brain. And he shows how the entire brain and a neural network of that time could learn to maintain stability homeostatics and, as a result, adapt to new environmental situations. So we need to rethink also reinforcement learning. Thank you.